There is a machine out there right now, drifting silently through the darkness between the stars, billions of miles from the nearest warm rock, running on the radioactive decay of plutonium, communicating home on a signal so faint it is weaker than the electricity produced by a single Christmas tree light bulb. It was built in the 1970s. Its computer has less processing power than the calculator sitting in a drawer in your kitchen. It has no repairman, no fuel station, no rescue mission waiting in the wings. And yet, against every reasonable expectation of what a 47-year-old machine launched before most of its current scientists were born should be capable of, Voyager 1 is still out there, still talking, still sending data. And what it has been sending back in recent years is so strange, so deeply unexpected, so fundamentally at odds with everything our best models of the universe predicted we would find in interstellar space, that some of the most careful, conservative scientists on the planet have run out of comfortable explanations. This is the story of the most distant object humanity has ever built, the impossible things it found, and the crisis it created for everything we thought we knew about the universe beyond our solar system. Let's begin by truly understanding where Voyager 1 is, because the numbers involved are so large that the human brain tends to just glide over them without actually feeling them. As of right now in 2026, Voyager 1 is approximately 25 billion kilometers from Earth. That number means almost nothing on its own, so let's try to translate it. If you drove a car at highway speed, without stopping, without sleeping, without slowing down for anything, it would take you more than 27,000 years to get there. A signal traveling at the speed of light, the fastest anything in the known universe can move, takes over 22 hours to reach Voyager 1 from Earth. That means when NASA's engineers want to send a command to the spacecraft, they transmit it, wait 22 and a half hours for it to arrive, and then wait another 22 and a half hours for the spacecraft's response to make it back. Every single conversation with the most distant machine humanity has ever built comes with a nearly 2-day delay. And yet, somehow, through NASA's deep space network of enormous radio antennas scattered across 3 continents, that conversation is still happening. Right now, today. A machine built in the Carter administration is reporting in from beyond the edge of the solar system, and what it is saying is extraordinary. Voyager 1 was launched on September 5th, 1977, 16 days after its sister spacecraft, Voyager 2. The 2 missions were designed to take advantage of an extraordinarily rare planetary alignment, a configuration where Jupiter, Saturn, Uranus, and Neptune were positioned so that a spacecraft could fly past all of them in sequence, using each planet's gravitational field as a slingshot to accelerate toward the next one. This alignment happens only once every 176 years. NASA could either take advantage of it in 1977 or wait until the 22nd century. They chose 1977, and in so doing, they gave humanity its farthest eyes. Voyager 1 swung past Jupiter in March 1979, discovering a thin ring around the gas giant that nobody knew existed, and finding 2 new moons, Thebe and Metis. At Saturn in November 1980, it found 5 more new moons and an entirely new ring called the G-ring. But even those discoveries were not the mission's greatest achievement. The greatest achievement was what happened after Saturn. Voyager 1 kept going. It left the solar system entirely, and it is still going now at approximately 60,000 kilometers per hour, more than 10 miles every second, heading deeper into the darkness between the stars. The spacecraft carries with it one of the most remarkable objects ever made by human hands, the Golden Record. A 12-inch gold-plated copper disc designed by a committee chaired by the astronomer Carl Sagan, the Golden Record is a message in a bottle thrown into the cosmic ocean. It contains greetings in 55 different human languages. It carries the sounds of Earth, waves breaking on a beach, wind through trees, a mother's first words to her newborn child, the crack of thunder, the song of humpback whales, human laughter. It carries 90 minutes of music, Mozart and Bach, Beethoven's Fifth Symphony, Chuck Berry's Johnny Be Good, a Navajo night chant, Azerbaijani bagpipes, a Peruvian wedding song. It contains 115 images of life on Earth, including diagrams of DNA and human anatomy and the mathematics of the universe. And it carries a pulsar map. Diagram encoded in the disk itself showing the precise position of Earth relative to 14 pulsars, allowing anyone who finds the record to calculate where it came from. The idea behind the Golden Record is both beautiful and haunting. That somewhere in the universe, something might find this disk floating in the darkness, decode it, and know that once, on a small planet orbiting an unremarkable star, creatures made of carbon and water became curious about what lay beyond their horizon and reached out. Whether anyone will ever answer is a question the universe has not yet chosen to resolve. But the fact that we asked at all says something important about what we are. What is happening right now with Voyager 1 is the convergence of 2 separate stories, each astonishing on its own, but together forming something that deserves far more attention than it is getting. The first story is one of human engineering, performing what can only be described as a miracle. The second story is what the spacecraft found when it got to where no machine had ever been, and what that data is forcing scientists to completely rethink about the universe. Start with the engineering miracle, because it is necessary to understand it before you can appreciate the full weight of the discoveries. On November 14th, 2023, the engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, received something deeply alarming from Voyager 1. The spacecraft was still transmitting. Its carrier signal was still arriving on schedule, indicating it was alive and pointed correctly at Earth. But the data stream, the actual content of the signal, had collapsed into meaninglessness. Where there should have been science readings and engineering status reports, there was now just a repeating pattern of ones and zeros. NASA's own team described it at the time as being like a phone call where the line is still connected, but the voice on the other end has been replaced by a dial tone. Voyager 1 was still out there. It just wasn't saying anything that made sense anymore. For 5 months, the JPL engineers worked through one of the strangest repair jobs in the history of technology. They were attempting to diagnose and fix a computer problem on a machine 24 billion kilometers away, using hardware whose designers had retired decades ago or were no longer alive, documented on paper blueprints that engineers had to physically dig out of archives. In March 2024, they sent a specific command, what the team called a poke, asking Voyager 1 to send back a complete readout of the Flight Data Subsystem's memory. The Flight Data Subsystem is one of the spacecraft's 3 onboard computers, the one responsible for collecting readings from the science instruments, packaging them into a form that can be transmitted, and sending them home. When the full memory readout arrived on Earth, 22 and a half hours after the poke was sent, engineers finally had their answer. A single chip, one RCA CD4 a CMOS SRAM chip, containing 256 words of memory, had failed. It had either worn out after 46 years of continuous operation or been struck by a high-energy cosmic ray particle. Nobody could say which. What they could say was that the chip held a critical section of the Flight Data Subsystem's own software code, and without that code, the computer could not function correctly. The chip could not be replaced. It is a piece of 1970s hardware sitting beyond the edge of the solar system. The only option was to work around it. What the engineering team at JPL did next was genuinely extraordinary. They took the corrupted section of code, divided it into pieces small enough to fit in the working portions of memory, scattered across the Flight Data Subsystem, rewrote all the internal cross-references so that the separated pieces would still recognize each other and run as a single coherent program, and then transmitted the first portion of this fix on April 18th, 2024. 22 and a half hours later, it reached Voyager 1, and on April 20th, 2024, for the first time in 5 months, Voyager 1 sent back readable engineering data. The engineers at JPL celebrated in a conference room in Pasadena. Bill Kurth, a research scientist at the University of Iowa who has been a member of the Voyager science team since 1974, since before the spacecraft launched, described the moment as being like watching a miracle. And he is a scientist. Scientists are not supposed to use that word, but sometimes reality earns it. The full restoration of science data took several more weeks, as the remaining pieces of relocated code were transmitted one by one, each requiring its own round trip of nearly 2 days to implement and confirm. By mid-2024, Voyager 1 was fully operational again, collecting and transmitting the kind of data that only it can collect, from a vantage point no other instrument in history has ever occupied. And that data, accumulated over years of operation in the interstellar medium, is what brings us to the second and far more unsettling story. Here is what scientists expected to find beyond the heliopause, the boundary where the sun's solar wind gives way to interstellar space. They expected to find something relatively simple and relatively quiet. The heliosphere, the sun's protective bubble of charged particles and magnetic fields, was understood to act as a shield around our solar system. Beyond it, in the interstellar medium, there should be thin, low-density gas drifting calmly between the stars, with a relatively predictable magnetic field pointing in a direction set by the broader galactic environment. The transition from the heliosphere to the interstellar medium was expected to be relatively sharp and well-defined. The space beyond was expected to be, in the truest sense, empty, cold, quiet, characterless, a dark, thin void between islands of stellar warmth. That was the model. That was what decades of theoretical astrophysics had predicted. And Voyager 1 has been systematically dismantling that model, piece by piece, since it crossed the heliopause in August 2012. The first shock came at the heliopause itself. As Voyager 1 approached the boundary, its instruments recorded abrupt, dramatic changes in particle density and magnetic field strength, not the smooth, gradual fade into interstellar space that the models predicted, but sudden, violent shifts, almost like stepping through a wall rather than walking out of a door. The temperature dynamics were completely unexpected. Instead of cooling as it crossed into the relative void of interstellar space, Voyager 1's instruments found zones of extraordinarily high heat. Charged particles near the heliopause were being trapped and compressed, creating pockets where temperatures were estimated at somewhere between 30,000 and 50,000 Kelvin, hotter than the surface of the sun itself. This wall of fire, as some researchers began calling it, was not what anyone had predicted. It was not supposed to be there, and the explanation for it, that the sun's magnetic field lines and the interstellar magnetic field lines were meeting at the boundary and undergoing magnetic reconnection, a process where field lines from opposite directions snap and reconnect, converting kinetic energy directly into heat, was something that models of the heliopause had badly underestimated. The magnetic field itself provided another surprise. Theory had said that when Voyager 1 crossed the heliopause, the direction of the magnetic field should sharply change, from the sun's spiraling outward field to the galaxy's own field, pointing in a different direction entirely. Instead, Voyager found that the magnetic field just beyond the heliopause was aligned in roughly the same direction as the field inside the heliosphere. The expected sharp transition didn't happen. What the data suggested instead was that the two magnetic fields, the sun's and the galaxy's, were somehow interacting, draping and reconnecting at the boundary in ways that blurred the separation between the two environments. This was, to use a technical term, completely unexpected. The boundary of our solar system was not a clean edge. It was a messy, turbulent, interactive frontier where two fundamentally different magnetic environments were pushing against each other and mixing in ways that current physics models were not accurately capturing. Then came the hum. In 2017, something happened with Voyager 1's plasma wave system, the instrument designed to measure plasma oscillations in the medium the spacecraft was traveling through, that nobody quite knew what to make of at first. The system began detecting a faint and extremely narrowband signal, not the intense plasma oscillations that Voyager had previously recorded when solar shock waves and coronal mass ejections from the sun created waves propagating outward through the interstellar medium. Those were loud, energetic, short-lived events. This new signal was completely different. It was quiet. It was constant. It had been going on uninterrupted since 2017. And when Cornell University astronomers Stella Koch-Ocker and James Cordes analyzed the data and published their findings in Nature Astronomy in 2021, the description they offered was quietly stunning. They described it as the faint, persistent hum of interstellar gas, a continuous low-level plasma wave emission at a frequency of approximately 3 kHz, narrower than anything previously detected, persisting across years of data, corresponding to Voyager traveling approximately 10 astronomical units through space. Though interstellar medium, far from being the characterless void that models had described, was humming. It had a voice, a low, steady, monotone voice, vibrating at a frequency no human ear could hear, but that Voyager's instruments could detect even in the near vacuum of the space between stars. Senior author James Cordes described the interstellar medium as being like a quiet or gentle rain. But the thing about rain is that it has structure, it has patterns, it is not nothing, it is something. And the discovery of this hum confirmed that the space between stars, which we had been calling empty, is in fact permeated by a continuous, structured field of plasma activity that our models had simply failed to predict. More data followed. In late 2024, as Voyager 1 pushed further into the interstellar medium, now more than 165 astronomical units from the sun, its instruments detected something that the 2025 and 2026 scientific literature has described with remarkable caution and a noticeable absence of confident explanation. Rather than finding the steady, predictable environment that models suggested the spacecraft would settle into as it moved further from the heliosphere's influence, Voyager detected a sharp surge in high-energy particles, followed by a sudden, unexplained shift in magnetic field direction. Not a gradual rotation, a jump. Almost as though the spacecraft had encountered a boundary or a structure that was not supposed to be there, something the models of the interstellar medium at this distance from the sun had not predicted. Published research examining Voyager 1's magnetic field data through mid-2025 describes the ongoing presence of intermittent turbulence in what should, by this point, be a pristine and undisturbed interstellar environment. The data suggests that Voyager 1 has not yet fully escaped the sun's influence, but the way that influence persists at this distance challenges the existing framework for understanding how the heliosphere interacts with the galaxy around it. Additionally, Voyager 1 has detected a broad electron density peak, a concentration of interstellar plasma that appears to be relatively stable, at approximately 160 astronomical units and beyond, with electron densities remaining constant at around 0.147 electrons per cubic centimeter. This is far higher than models of the pristine interstellar medium at this distance predicted. Something is out there, denser than expected, more active than expected, more structured than expected. And Voyager 1 is the only instrument humanity has ever placed there to measure it. There is one more dimension of this story that has not received nearly enough attention, and it comes from asking a very simple question. How much longer can Voyager 1 keep going? The answer is both incredible and heartbreaking. The spacecraft runs on 3 radioisotope thermoelectric generators, RTGs, that convert the heat produced by the natural radioactive decay of plutonium-238 into electricity. At launch in 1977, those generators produced about 470 watts of electrical power. Plutonium-238 has a half-life of 87.7 years, which means that power output declines slowly but continuously. To compensate, the JPL team has been turning off non-essential systems one by one for decades. Heaters, instruments, subsystems, trying to preserve enough power to keep the remaining science instruments and the transmitter alive. By 2025, only 2 science instruments were still operating, the magnetometer and the plasma wave system, the very instruments that detected the hum and the magnetic field anomalies. NASA estimates that the RTGs will drop below the minimum power threshold needed to operate any systems at all somewhere in the early 2030s. When that happens, Voyager 1 will go silent. For the first time in nearly 60 years, it will stop talking to us, and whatever it passes through after that, whatever structures and fields and densities and mysteries wait further out in the interstellar medium, will go unrecorded, at least by any instrument humanity currently has in place. What makes this not just sad, but scientifically urgent, is that we have nothing behind it. There is no Voyager 3. There is no successor mission already on its way. NASA's most recent heliophysics decadal survey, released in 2024, looked at the proposal for an interstellar probe, a dedicated mission designed to travel beyond the heliopause with modern instruments, and did not prioritize it. China is reportedly pursuing its own interstellar mission, but the details are sparse and timelines are uncertain. What this means, in practical terms, is that when Voyager 1 goes silent in the early 2030s, humanity's direct sensory access to the interstellar medium will be reduced to Voyager 2, which is trailing behind on a different trajectory and is also running out of power. After that, there will be a gap, potentially a very long gap, before any new human-made instrument reaches the distances where these phenomena can be directly measured. Everything Voyager 1 is discovering right now is data we may not be able to replicate or build on for a generation or more. The impossible things Voyager 1 found are not impossible in the sense of violating the laws of physics. They are impossible in the sense that they should not exist according to the models we built to describe reality. And their existence tells us that our models are wrong in ways we do not yet fully understand. The heliosphere boundary is not a clean edge, but a turbulent, magnetically complex frontier. The interstellar medium is not empty silence, but a structured, humming, active plasma environment. The magnetic fields out there are not pointing where we expected. The particle densities are not what we predicted. The temperature dynamics at the boundary were not what our best theories said they should be. And there are structures and boundaries further out and well past the heliopause that appeared in the data as sudden shifts and surges that current models have no clear accounting for. Every one of these findings is a message from a spacecraft older than most of the engineers now working on it, transmitted on a signal weaker than a fridge light, received after traveling at the speed of light for more than 22 hours, telling us that the universe beyond our solar system is stranger, richer, and more complicated than we assumed. There is something almost philosophical about what Voyager 1 represents. It is the most distant thing humanity has ever made. It carries within it, in the form of that golden record, a declaration of who we were when we sent it, what we valued, what sounds moved us, what we hoped the universe might contain. And it is sending back, from the edge of everything we have ever known, evidence that the universe is more surprising and more mysterious than we counted on. The hum it detected in the interstellar plasma is the universe talking back. Not in any intelligible language, not in any code we have learned to decode. Just the quiet, persistent vibration of a cosmos that turns out to be far less empty and far less predictable than our models ever gave it credit for. Voyager 1 did not find what we expected. It found something more interesting. And with a failing power supply and the early 2030s approaching like a closing door, it is still out there right now, instruments running, transmitter pointed home, sending back the last data it will ever collect from a frontier that no human eye has ever seen and that no human hand has ever touched. Whatever it is finding out there in the space between the stars, it is finding it for us. And the least we can do is pay attention.